Right now, sitting in a data archive at Caltech, there's a number that 10 years ago would have sounded like science fiction. 390, not a theory, not an estimate. 390 confirmed collisions between the darkest, densest objects in the universe, each one a moment when two black holes found each other across billions of light years of empty space and tore a ripple through the fabric of reality itself. And that number just grew by 161 in a single afternoon. I want you to sit with that for a second, because this is not a story about one discovery. It is a story about what happens when discovery stops being rare, when the extraordinary becomes routine, and when routine, if you look closely enough, hides something nobody expected to find. Because buried inside those 161 anew detections were two collisions that should not have been possible. Two black holes that, according to everything we understood about how black holes form, simply should not exist. And what scientists found when they looked closer is that some of the darkest objects in the universe have been hiding in plain sight, disguised inside a catalog that everyone assumed they already understood. Stay with me, because this is the story of how astronomy quietly, without most people noticing, became a completely different science. To understand why this catalog matters, you need to go back to September 2015. That month, for the first time in human history, an instrument on Earth detected a gravitational wave, a literal ripple in space and time itself, produced more than 1 billion years ago when two black holes spiraled into each other and merged. It was not light. It was not radio waves. It was space-time physically stretching and compressing as the wave passed through the LIGO detectors in Washington and Louisiana. Albert Einstein had predicted this a century earlier and doubted it would ever be measured. It was, and it earned a Nobel Prize. For years after that first detection, every single gravitational wave event was a headline, a rare, precious data point. Scientists studied each one individually, sometimes for months, extracting every possible piece of information from a signal that might never repeat. That era is over. On May 26, 2026, the LIGO-Virgo-KAGRA collaboration, 3 detector networks spanning the United States, Italy, and Japan working together as one instrument, released something called GW241011, the 5th Gravitational Wave Transient Catalog. It added 161 newly confirmed signals, all detected between April 2024 and January 2025, in a single 10-month observing run. That pushed the total number of confirmed gravitational wave detections in human history to 390. 10 years ago, that number was 1. Now it is 390, and during the most active stretch of that observing run, the universe was producing 3 to 4 detectable black hole collisions every single week. Let that sink in. Every week. Somewhere out there, multiple times every week, 2 black holes are finding each other and merging, and we are now sensitive enough to hear it happening from Earth. Leo Tsukada, who co-chairs the collaboration's science working group, put it plainly. Nearly 400 gravitational wave events have pushed astronomy into what he called a new era of statistical astronomy. Not the era of the single spectacular discovery, the era of the population, the era where you have enough data points that the interesting story is not any one collision, it is the pattern hiding underneath all of them. And that pattern is where this story turns from remarkable into something genuinely strange. The first record buried in this catalog belongs to a signal called GW241011, detected on January 14th, 2025. It came from 2 black holes, 32 and 34 times the mass of our Sun, colliding more than 1 billion light years away. What made it extraordinary was not its size, it was its clarity. GW241011 registered a signal-to-noise ratio of 76.9, the highest ever recorded for a gravitational wave event in history. Here's why that number matters. A clean signal means clean physics, and this signal was clean enough that scientists used it to test something Stephen Hawking proposed in 1971. Hawking's area theorem states that the total surface area of a black hole's event horizon can never decrease during any physical process, no matter what happens to it. It is one of the foundational predictions of black hole physics, and for over 50 years, it existed as pure theory, elegant on paper, untestable in practice. Using GW241011's exceptional data, researchers confirmed Hawking's area theorem holds true at 99.9 or 99% confidence. Not almost certain. Not highly likely, a number so close to absolute certainty that in physics, we simply call it confirmed. A prediction made by a 29-year-old physicist working with pen, paper, and pure mathematics, sitting untested for more than half a century, verified by a chirp of space-time captured 1 billion light years from its source. And that was just one signal. A second record came from a collision called GW241011 detected June 15th, 2024. 2 black holes, roughly 26 and 30 solar masses, merging more than 3 billion light years away. This signal did something no gravitational wave detection had ever done before. Scientists pinned down its location in the sky to within just 6 square degrees, the tightest spatial constraint ever placed on a gravitational wave source in the history of the science. Why does location matter so much? Because if you know exactly where a collision happened and how far away it was, you can use that measurement completely independently of light, of telescopes, of anything electromagnetic, to calculate how fast the universe is expanding. Xin-Yu Chen, who led that analysis, said the improved data delivered roughly 25% better precision on that measurement. 25% from a single well-placed signal, feeding into one of the most stubborn unsolved problems in modern cosmology. A disagreement about the universe's expansion rate that has frustrated physicists for over a decade and still, even now, refuses to fully resolve. But none of that, not the clarity, not the location, not even Hawking's theorem, is the part of this story that should actually keep you up at night. Because buried inside those 161 new detections were 2 signals that broke the rules entirely. They are called GW241011 and GW241110. One detected in October 2024, roughly 700 million light-years away. The other in November 2024, at a staggering 2.4 billion light-years. And when researchers examined the black holes involved in these 2 collisions, something was wrong with their spin, wrong with their mass ratios, wrong in a way that could not be explained by the standard story of how black holes are supposed to form. Here is that standard story. A massive star runs out of fuel, it collapses under its own gravity, it becomes a black hole. 2 such black holes, born in isolation from 2 separate dying stars, eventually find each other, spiral together, and merge. That is the textbook formation pathway. That is what nearly every black hole collision we had detected before this catalog appeared to follow. GW241011 and GW241110 did not follow it. Carl Johann Haster, the researcher who analyzed these 2 signals, said their spin and mass characteristics are inconsistent with an origin in an isolated stellar binary. And then he said something that should stop you cold. Binaries like these had been predicted, given earlier observations, but this is the first direct evidence for their existence. Predicted, theorized, suspected, and now for the first time in the history of the science, confirmed. What Haster is describing is something scientists call second-generation black holes. Black holes that are not the direct product of a single collapsing star. They are the product of an earlier merger. A black hole born from 2 other black holes colliding, surviving that collision, and then, later, colliding again with something else. A black hole with a family history. A black hole that has already lived through one violent, universe-shaking event before the one we just detected. For that to happen, you need very specific conditions. You need dense environments where black holes are packed close enough together that repeated collisions actually become statistically likely. Places like globular clusters, tightly packed spherical swarms of ancient stars, or the crowded, chaotic centers of galaxies, where gravity concentrates enormous numbers of massive objects into a comparatively small volume of space. In those environments, a black hole is not guaranteed a single quiet fate. It can merge, survive, drift, and merge again and again. This means some of the black holes cataloged in GWTC 5.0, hiding among 390 detections that most people will only ever see as a headline number, are not simple, single-generation remnants of dead stars. They are repeat offenders, objects with a violent past that predates the very collision we use to detect them. Black holes built from black holes, hiding inside a dataset that, on the surface, looked like more of the same. I want to be clear about what this does and does not mean, because the story is remarkable enough without exaggeration. This catalog does not prove that every black hole with unusual spin is second generation. It does not settle the exact fraction of the 390 confirmed events that came from repeated mergers versus isolated stellar collapse. Even the researchers involved say that determination requires more data and better models of what each formation pathway should actually look like in the numbers. What the catalog does prove, for the first time with direct observational evidence, is that this hidden population is real, that it exists, that some of the darkest objects in the universe are quietly building themselves through repeated violence in the crowded centers of star clusters and galaxies, and we only just learned how to recognize the signature they leave behind. Here's the detail that makes all of this even more staggering. The 161 new signals in this catalog were not collected over decades. They came from a single 10-month observing run between April 2024 and January 2025. That one stretch of data, combined with the run immediately before it, accounts for roughly 75% of every single gravitational wave event ever detected since 2015. 3/4 of everything we have ever learned about colliding black holes came from less than 2 years of listening. That is not a coincidence of timing. That is a detector network that got dramatically better at hearing the universe, and it is only going to get better from here. The LIGO detectors in Hanford and Livingston, along with Virgo in Italy and KAGRA in Japan, are currently offline, undergoing sensitivity upgrades between observing runs. When they come back online, they will hear farther, clearer, and more often than they ever have before. The pipeline that produced 390 detections in a decade is about to get faster, which means the next hidden population, whatever it turns out to be, is not decades away. It might be sitting in the very next catalog. None of this would have been possible without something else buried in the fine print of this release. A new computational pipeline, developed at the University of Glasgow, accelerated the signal analysis process by more than 1,000 times compared to previous methods. Daniel Williams, who led that work, pointed out something easy to miss in all the excitement about black holes. At 3 to 4 events a week, the old analysis tools simply could not keep up. The discovery was not just astronomical. It was computational. Somewhere in a server room, code was rewritten so that human beings could keep pace with a universe that had started talking faster than we could listen. Now step back from the individual numbers for a moment, because I think this is the part of the story that actually matters most. 10 years ago, a single gravitational wave detection was a global headline and a Nobel Prize. Today, the interesting discovery is not a single chirp of space-time. It is the shape of the crowd. 390 data points laid side by side, mapped by mass and spin and distance, are finally dense enough to ask a question no single detection could ever answer. Not, did this happen? But what is the universe building over and over in the dark, dense centers of its oldest star clusters, and how long has it been doing it without us noticing? We are no longer just detecting black holes, we are starting to read their biographies. Some were born once, quietly, from a single dying star, and merged once, and that was the whole story. Others, like the two hiding inside GW241011 and GW241110, had already lived through one collision before the one that finally let us see them. They carry the imprint of a violence in their past, an imprint written into their spin and their mass, invisible to any telescope, readable only in the way they shook space-time on their way to their second death. 390 black holes, a hidden fraction of them built from earlier versions of themselves, and a detector network about to get sharper, listening for the next one, right now, while the machines are quiet, being upgraded, waiting to hear the universe's next confession. If this is the kind of story you came here for, the actual data, the real discovery, told with the weight it deserves and none of the invention it doesn't need, subscribe right now, because the detectors are coming back online. The next observing run will produce more signals faster than any run before it, and somewhere in that flood of data, there is very likely another black hole with a hidden past, already merged once, waiting for the moment it collides again, and this time, we're listening closely enough to hear exactly what it's been hiding. The universe just produced 390 confessions. Some of them were lying about how simple they were. We are only now learning how to tell the difference. Stay with us, because the next signal is already on its way.